Hey folks, my name's Ritika and I am a software engineer at Confluent. I've been working here, I think, almost 2 years on the Kafka storage team. And today I'm going to tell you guys a little bit about the woes of degraded storage and how we automatically detect and remediate it in our Confluent Cloud. Okay. So I thought I'd start off by giving you guys a brief introduction of how Kafka actually writes to the log and how that data is actually saved on the disks of the broker. So suppose we start off with a cluster that has, say, n brokers. As you can see in the diagram, there are disks allocated to each of these brokers. Whenever we want to write data to these brokers, we would need to spin up a couple of producers to write data to a topic. And whenever we want to read data from these topics, we would need to spin up a couple of consumers to do so. So now that we've kind of gone over that general pipeline, produce, consume workflow, I thought we can break it down a little bit further into how we are actually saving this data on the broker. So one thing to keep in mind is when you're writing to a topic, you're actually writing to a set of topic partitions. And a broker can be either a leader or a follower for these topic partitions. When a broker is the leader, that means it's servicing all of the produce and consume requests directly, and it's updating the log based off of those. And when the broker is a follower, that means it's following along with whatever the partition leader is doing. Okay, so let's break this down even further. Each topic partition can actually be broken down into different segments. So a segment is, well, a segment of data that can contain some designated capacity of messages. In this toy example, we have about, I think 3 messages per segment, and they're named based off of the start offset of each of the messages in this segment. So that's why we have segment 0, segment 3, segment 6, and then segment 9. Yeah, and when you're writing to a segment, you are actually writing to 3 different files. So the first file that we're writing to is the segment log file, and that stores all of the messages up to a specific offset. So segment 0 would contain record 0, record 1, and record 2. Then we have the index file, which stores a mapping of the message ID to the offset. And then finally, we have the time index file, which stores a mapping of the message timestamp to the offset. So whenever we're writing data or producing data, we're actually writing to these segment files, these 3 segment files. Okay. So suppose that segments 0 through 6 are already filled. All of the data has already been, all the record slots have already been taken up, and there's no more space to write to those segments. Then we refer to them as non-active segments because there's no space to write to them anymore. Conversely, segment 9, we have 1 remaining open slot over here, so we refer to it as the active segment, so the segment that we're still actively writing to. Okay. All right, so let's break this down again by starting from the produce workflow. So we say we want to produce a message to a specific topic. That request gets routed to this broker, which happens to be the leader of topic partition 1. And we want to produce whatever message we were given. And we look for the active segment. We find that segments 0 through 6 are already filled. So we end up picking the active segment, which is segment 9. And we insert that message in that last slot, the last open slot over there. And that's written over there. So now you might be thinking, okay, what happens next now that segment 9 is filled? What do we do? So basically we take those 3 files that are associated with the segment and we close them. So segment 9's log, index, and time index files are all closed, and we open them again in read-only mode. And we instead create a new segment file called new segment files associated with segment 12, which is the new current active segment now. And this whole process is called rolling the active segment. Yeah. So now that we kind of have a general understanding of how we end up eventually writing this data to the broker disks, I wanted to break down exactly how we measure the performance of all of these operations and make sure that our cluster is healthy and operations are going exactly as we expect. So the first thing we look at is end-to-end latency. So this is pretty simple. It's the total amount of time that it takes to produce and consume a record from end to end. So let's break down this graph over here. We're looking at the P99, and for those of you who don't know what that means, that just means that we're plotting the value that is at the top 1%. So that means 99 out of 100 requests have had like lower values in this, but we're plotting the value that's one higher. So those are the values that we plot. The x-axis in all of these graphs is going to be over time, and the y-axis is always going to be in milliseconds. And as you can see, there are multiple different lines because we plot by broker. Yeah, so in a typical healthy cluster, we expect this value to kind of oscillate between like maybe like tens of milliseconds. So here you can see this is, for this particular cluster, it's between like 10 to 30 milliseconds, and you know, it's looking pretty good. These produce and consume operations are happening pretty quickly. Okay, so the other latency that we want to look at is the storage latency, or the segment append time. This is essentially the amount of time it takes to write to disk or to basically append a record to the active segment. Yeah, so to look at this graph over here, again, x-axis is time, y-axis is milliseconds, and it's again broken down by broker. We can see on average we are about less than 1 millisecond. It takes about less than 1 millisecond to actually write to disk. And this is pretty ideal. We definitely don't want to take too long to write to disk, and this is what we'd expect from a healthy cluster. And you might also be wondering why we're looking at storage latency separately from end-to-end latency, given the fact that you might be thinking like, shouldn't end-to-end latency anyways cover storage latency because we're just measuring the segment append time, which is part of the produce consume workflow. Well, we want to look at this specifically because we're going to be looking for correlations between the storage latency and the end-to-end latency to make sure that the storage is the reason for these spikes that we're seeing in end-to-end latency. So that's why we're looking at both of these different factors. Okay. All right. So now that we have a general understanding of how we actually write to the log and write to the disk, and what are the expected measures whenever the cluster is healthy, we can finally talk about what is degraded storage and what that actually means. So for simplicity, we're going to start with an example where Kafka is running on the cloud. So one of our cloud providers, could be GCP, AWS, or Azure, or whatever, provides us with disks for each of our brokers. But what happens when that disk goes boom? So what we end up seeing is maybe a partial or fully unavailable disk. The disk that's provided is kind of spotty, and it's not functioning as we expect. If this issue is spread across multiple disks, so across several brokers, this could even lead to cluster unavailability, which definitely we don't want. And the way that partial, fully unavailable disk kind of devolves is that we end up having slower reads and slower writes on the broker when we're not hitting the file system cache. So for those of you who are not aware of the file system cache, that's just when we're looking at recent reads or writes. So those may succeed and have normal latencies, but we're probably not hitting the cache. Our latencies are going to be pretty impacted, and we're going to see higher end-to-end latencies and higher storage latencies. Yeah, so kind of breaking this down again, we're going to look at the end-to-end produce consume latency, P99 over here. Again, this is over a 24-hour period, and the y-axis is milliseconds. And as you can see, there's like a pretty notable spikes at about like 1.5 seconds, which is a pretty long time for like produce, consume, end-to-end to take. Like I said earlier, we expect this to be in the order of like tens of milliseconds. And one other thing to notice is that this isn't consistent, there aren't consistent spikes, right? Like for like the first couple of hours, we see a lot of like really big major latency spikes, but then we have like a brief respite for like about 6 hours where we don't notice any of these like high latency spikes, but then it returns again with a vengeance, and yeah, we see them again. Okay, and this is the corresponding storage latency graph. So as you can see, the spikes themselves are actually corresponding, kind of indicating the correlation between the storage latency and the end-to-end latency, where like, you know, degraded storage is the cause for those like spikes that we were seeing in that other graph. So over here, we see a pretty big spike of about 5 seconds around like 12 o'clock PST, which is pretty bad for it to take 5 seconds to write a record to disk. So, but yeah, we, again, like I mentioned earlier, would expect this to be under like 1 millisecond, to not ideally take too long. Yeah, so this is what it looks like when we have an instance of degraded storage. Okay, so I've talked at you guys a lot about, you know, like how we see degraded storage and what are some of the symptoms of degraded storage that we see, but you might just be thinking like, oh, you know, like shouldn't the cloud provider be giving us good disks? Like shouldn't this, you know, like 99% of the time, like they say that they're gonna be giving us like consistently good disks, and we should be expecting like good performance, et cetera, from them. But, so I just wanted to pose this question to all of you. How many incidents of degraded storage do you guys think Confluent Cloud has experienced in the last 30 days? And if you guys have been to the 10x talk and you already know the answer, abstain from answering, please. But yeah, does anyone have a guess? Like on the order of thousands of clusters? Okay, in the last 30 days? Okay. Okay, that's actually a little high. Yeah, a couple of hundred is more accurate. It's 500 incidents in the past 30 days, but couple thousand. But still, 500 is a pretty big number for just within 30 days when we're expecting our, like whatever disks we're getting to be, you know, good, reliable 99% of the time. Yeah, and that averages out to about 6,000 incidents per year, which is kind of crazy, kind of big number. So just kind of wanted to give you guys that context as to why this is something that we invested into and why degraded storage is important. Okay, so now that I've kind of broken down those bare bones of degraded storage, let's talk a little bit about the two main classes of it. So first we have persistent degraded storage. This refers to any long-term instances of degraded infrastructure. So, you know, this will be on the order of like several hours, maybe several days. You know, it's very long-term as the name indicates. We also noticed that the end-to-end latencies are also not consistently bad. So remember that example that I showed you guys earlier where there was like, you know, maybe the first like 8 hours, we saw like a lot of like large intermittent spikes, but then, you know, there was a brief respite for 6 hours and then we saw them again. So maybe those end-to-end latencies aren't always bad, but, you know, and maybe even the storage latencies will temporarily recover or get a little bit better, but they never fully return to that good state that they were in before the disk faced some kind of degradation. And oftentimes we may even have to replace the disk in order to mitigate those kinds of incidents when it's a serious case of persistent degraded storage. Okay. So I wanted to show you guys a couple of graphs to really demonstrate what that would look like. This, I think, is over a period of about like maybe 20-ish hours. So as you can see, like first couple hours, things are looking pretty good. And again, x-axis is time, y-axis is milliseconds. End-to-end latencies are like looking fine, but then we notice a brief spike at about, I would guess maybe 8:39-ish at 200 milliseconds. And that, you know, maybe not immediately cause for concern, like if it's just isolated, but, you know, once we started seeing that like large spike at 600 milliseconds, maybe an hour later, like at like 10 or 10:30 or something, that's when it's actually cause for concern, when we're seeing those kind of large unisolated spikes, where it spikes to 600 milliseconds, and then after that, we kind of average end-to-end latency between like 200 to 300 milliseconds. So that's definitely not good when we're expecting that value to be within the order of tens of milliseconds, right? And you know, you might be thinking, okay, you said like one isolated incident is bad, but when it's persistent, it is definitely going to end up showing on the user's end, and we definitely don't want that. Okay, and then you can see the corresponding storage latencies over here as well, where we notice that correlated large spike at about 1.1 seconds to write to disk, definitely not ideal. And then after that, it averages out around 500 milliseconds to write a record to disk. Again, definitely not ideal, definitely not something that we would want, and definitely something that we need to address. Okay, the other kind of degraded storage is transient. So this is a short-term instance of degraded infrastructure, as the name implies. So this is instead on the order of minutes or on the hour, or order of like at most maybe an hour. And this may auto-recover within a short period of time due to some other transient factors. Maybe this is just like, like a small network blip or something. So that's kind of the pattern that we've noticed with this kind of degraded storage. So when we look at this graph over here, so instead of being over several hours, this is about maybe just 1 hour time window. When we look at the end-to-end latency, around 8:32, disaster strikes, we're getting end-to-end latencies of like spikes at about like 19 seconds. 19 seconds is a lot of time to produce and consume, to produce and consume a record. So definitely not ideal. Again, around 8:32, you can notice the same kind of degradation in the storage latency. It's taking about like 18 seconds to write to disk. So definitely not ideal and definitely correlated between the two incidents. But the interesting thing here is that we notice that this actually resolves itself within like 10 minutes, not because of our mitigation, but just because of the type of degraded storage this is. It just self-resolves within 10 minutes. But the values, or like the extent of this degraded storage is significantly worse than the extent of the persistent degraded storage, but both are bad. So one is really bad for a short period of time, but persistent is kind of medium bad for a long time. So pick your poison. Okay, so now that we have a good understanding of what is degraded storage and the different classes and how we got that data to disk, let's finally talk about how we actually mitigated degraded storage. Okay, so I know the initial example I gave was related to the cloud, but I wanted to also provide some context on how we can resolve or mitigate a similar issue on-prem. So first we would want to identify any brokers with bad disks, and we can reassign leadership using one of the bin Kafka scripts, like Kafka reassign partitions or the Kafka leader election scripts. Okay, so let's walk through an example of that. Say we have two different brokers. We have broker 1, which happens to be the leader for topic partition 1, and a follower for topic partition 2. And then we have broker 2, which is a follower for topic partition 1 and a leader for topic partition 2. Broker 2's disk goes boom. And then what happens? In order to mitigate this, like I said, you can use one of the bin Kafka scripts. And if you'll notice, we had some leader election, and broker 1 happened to be elected as the new leader for topic partition 2. And instead, the old leader, which was broker 2, was made the follower for topic partition 2 over here. Yeah, so that's one quick example of how you would be able to minimize the impact to performance in an on-prem scenario. Okay, let's talk about how we handle this in C Cloud. So first, we have created some mitigation to, or like this pipeline to automatically detect any problematic brokers and with like bad disks or instances of degraded storage. We've created this new state called degraded versus like healthy, which will allow us to trigger like said mitigation. And if it's a case of persistent degraded storage, we may even need to replace the disk. So to kind of, I guess, bring it all together, let's walk through the pipeline. So first we set up some monitors for the unhealthy brokers. And we're using the same latencies that I described earlier. We're looking at the end-to-end produce consume latency, and we're also looking at the storage latencies to kind of determine whether this broker is unhealthy due to degraded storage. If we notice that it is, we use this tool called Shoreline, which hooks into this monitor, and we'll be able to run some kind of script that we provide it with when the monitor reaches like some certain threshold. So the mitigation that we have it set up to do is to change the broker state from healthy to degraded. Okay. So then what happens next? We either are waiting for the the affected broker's disk to recover itself, or perhaps we need to replace the disk or take some other actions. But whatever it is, the unhealthy broker's disk will eventually recover. And once it does, Shoreline will kick in and recognize, based off of that monitor, that the broker has recovered, and it will mark the recovered broker as healthy again. And you know, it's a loop. We continuously keep monitoring for unhealthy brokers and keep applying this remediation whenever it's applicable. Okay. So now let's dive a little bit deeper into how it looks when we change the broker state. So say we start off with this broker 0, which happens to be healthy and happens to also be the leaders for topic partitions 1 and topic partitions 2. So currently the in-sync replicas for each of these topic partitions are as follows. So it's brokers 0, 2, and 4 for TP1 and brokers 0, 1, and 3 for TP2. Okay, disk goes boom, now what? Well, our monitor detects this, and we trigger the remediation, or Shoreline runs the script, which will then mark this broker state as degraded. So what does that look like? So now topic partitions 1 and topic partitions 2 actually end up becoming followers. However, they're a special kind of follower. They're silent followers. So it's not part of the in-sync replicas because we want to reduce the performance hit for produce for like instances in which the producers have ACK equal all. So basically that's why broker 0 is not in the in-sync replicas for those anymore and kind of just silently continues to catch up. Okay, so now what happens now that broker 0 recovers? Shoreline notices this, and based off of the monitor that we've hooked it up to, and we mark this broker as healthy. And now, topic partition 1 and topic partition 2 are active followers, so they're not silently following along, and they rejoin the ISR over here. So that means that they're also eligible to become a leader for these topic partitions again later on if there is a leader election for it. Yeah. Okay, so now that we've kind of gone through what it looks like to mitigate degraded storage and what that whole pipeline looks like, let's talk about the impact that we've actually seen in production for this. Okay, so the battle, oh, okay, I should give you guys a fair warning. There are emojis involved, but, you know, Gen Z things. But the battle against degraded infra begins, and this is an instance of transient degraded storage. As you can see, we're starting to get a little bit nervous. You know, our latencies are starting to climb, and then they hit the peak over there because our mitigation finally kicked in and the battle begins. And, you know, Shoreline has kicked in, marks the broker as degraded, yada, yada, yada. And, you know, our latencies have recovered and things are looking good. We're in the order of tens of milliseconds, which is exactly what we want. And all of this detection happened within just 5 minutes. So we've only had 5 minutes of some small amount of impact. But we got to it. Okay. This is an example of persistent degraded storage. So again, these are the end-to-end latencies. This is, I think, probably like a 1 hour period, but the degradation had been going on for a little bit longer. I just happened to show like the small window in which we, to like really emphasize like the mitigation part. Okay, so we're starting to get worried once we see, you know, end-to-end latencies are taking like maybe 500 to like 700 milliseconds, definitely cause for concern. But then, you know, our mitigation kicks in and we mark this broker as degraded. It is no longer a leader for these topic partitions. And we start to immediately notice the latency impact. Before the latencies were high for like all these other brokers, but then, you know, the impact is reduced. And then finally, when the broker recovers, you know, it rejoins and everything's all good. Latencies are looking good and we're happy about it. Okay, and finally, I wanted to show you guys an example of storage latencies as well. So you'll notice over here, we're looking at the P99 storage latency. And just as a reminder, we're measuring this value where we're taking the value where 1 out of like 100 requests would have this value. So 99 out of 100 requests will be less than this value. And we're recording this, I think, like maybe every minute. But when you initially look at this graph, like you might be thinking, okay, like, you know, there's nothing wrong with it. Like everything seems to be like under 1 millisecond. Isn't that what we want from storage latency? You know, we only see like this small, tiny spike above like 1 millisecond. So it's like 1.4 milliseconds. And you might be thinking, okay, like, so what? Like this doesn't seem to be a big deal. This is what we want, right? But you would be wrong. This is a problem in disguise. And the reason why is because we're not looking at tail latencies. So tail latencies actually matter because if you notice over here, we have this really big spike at 1 second, just like straight off the bat. So like if you compare both of these graphs, like in the beginning, like you notice sub 1 millisecond latencies in the P99 graph, but in the P999 graph, you immediately notice this huge spike of like 1 second to write to disk. And you might be thinking, okay, this happens like 0.1% of the time, do we care? But for like performant systems, we really need to think about these tail latencies because even if this is only happening like 0.1% of the time, or like in 0.1% of cases, like this is something that we need to consider and make sure it doesn't happen, because otherwise we are overlooking the actual problem. But you know, we were looking at the P999 latencies, so we were all good. Our mitigation triggered, and you know, storage latencies reduced, and they got to a level that we like, even in the P999, and cha-ching, we're happy. Yeah, so kind of in summary, there are two different types of degraded storage, persistent and transient. So persistent, as a reminder, on the order of hours or days. Transient is on the order of like minutes, maybe at most an hour. Degraded storage often actually goes unnoticed, and you'll notice it definitely from like your end-to-end latencies, but you might look at your P99 storage latencies and think, okay, like everything's fine. They're not fine. you need to check your tail latencies as well to really make sure that you find and identify the problem. And finally, just don't let degradation bring you down. That's all I had for you guys. And I want to give a quick thank you to everyone on the Kafka storage team and the Kafka performance team for all their help with this project. Yeah, did anyone have any questions? Thank you.